Okay, so in chapter 7 challenge problems, we still have 58 to 766. So perhaps we don't have enough time to finish all of them today. So maybe we finish half of them, and then we spend a little bit time in chapter 8, clarifying some concepts. Okay. And all these questions, I believe, they deserve a discussion. So let's have a look. For you guys, this is like 3, 4 weeks ago. Um, yeah, so let's just read the question and let's do the questions together. Okay, any one of you has any idea? Then you can open up your mic and talk to me, okay? So first question, you can read it. I'll give you some time to read it and see if you guys have any idea. This is not a hard one. Okay, does anyone have any idea? We have 45 dimes, right? 45 coins, and we're given a ratio. So this isn't a hard one. We know the total number, and then we know the ratio. So we can calculate the exact numbers of each pile, right? And how are we gonna do that? Anyone?
Is the LCM for both three fractions,
Mm-hmm.
and it's
Great.
12. And it's
Right.
12.
Mm-hmm. So what do we do about this ratio?
We just multiply, like, yeah. 1 over 6 times 12, 1 over 3 times 12, and 1 over 4 times 12.
Very nice. Very nice. Okay, very good. So Jerry, Emma, see if you guys have the same idea. When you so notice that, for example, this question, if you know the ratio in integers, then we can just add the integers up and divide 45 by it, right? You guys remember? Say 1, 2, 2, 2, 3. That means you have one. If you have one coin in the first pile, then you have two coins in the second pile, and then you have three coins in the third pile, right? So that way, remember, we're just gonna add it up because in total, we're gonna have like 6 coins as a group, right? And then we're gonna just divide 45 by 6. Here it's not divisible because I'm just giving random numbers, right? Say that is 1, 2, 2, 2, 2. Then we add them up. That's 5 parts, you could say, right? One part in the first pile, two parts in the second and third pile. So in total, you would have 5 parts, right? And then when you divide 45 by 5, you will see that one part is 9. And that means you have 9 coins here, 18 coins here, 80 coins here. Okay, Jerry, Emma, do you guys remember this? You add them up, right? Okay. So Emma, does that sound okay for you? You add the ratio up? Yeah, okay. So if you don't have integers, you can change them into integers, right? In this case, they're fractions. So the denominators, we have 6 and 3 and 4. And obviously, if we time them by 12, because the least common multiple here is 12, right? So if we time them by 12, we can change all of them into integers. Okay, so we've done a similar question before. It will be where? Let me show you. We did a very, very similar question, exactly the same almost before. Okay, couldn't find it. Anyway, okay. Another way to do this is that so Albert, see if you remember this. We don't even have to change this into integers. we can just deal with fractions. We can still add them up, just just as if they're integers, still add them up, divide 45 by it, and multiply the proportion, like multiply the ratio back, right? Just as if you're doing the integers. Okay, so let's do both ways, and hopefully you guys can remember this time, because we've done a similar question last time, like a ratio with fractions. So first we can multiply everything by 12. And this way will give you 2 to 4 to 3. And then we just add them up, divide 45 by it, right? So we add them up, and that's 9. And we divide 45 by 9, and that'll be 5. So that tells us that there were 9 parts in total, and each part is 5, right? So eventually we just time it back. So everything times by 5, that means we have 10 to 20 to 15. Okay, so these will be the numbers of dimes in this case, yeah, in each pile, right? First pile we have 10, second pile of 20, third pile we have 15. Okay, Jerry, that makes sense? The question is asking us to find out the number of dimes in the least number in the pile with the least number of dimes, right? So to find out the least, that's 10. So we just use 10 as the answer. Okay, another way to do this is that we don't even have to change this into integers. We just deal with fractions. We do the same way, right? Remember that if you have a ratio, you always add them up, right? And divide 45 by it. So we can just add the fractions up. It was an example problem, I believe. It was an example problem, right? We've done same question before. Let's see. Which problem was it? Okay, can't find it. Okay. Anyway, so we've done a similar one before. Okay, so we add the ratios up. In this case, we can just add 1/6 to 1/3 to 1/4. Okay, so we add all of them up, and then we get common denominators. So that's 12, and that's gonna be a 2 for 1/6, a 4 for 1/3, a 3 for 1/4, right? So that means we have 9/12. And we simplify, that's going to be 3/4. Okay, so we add all the ratios up, we get 3/4. Okay, in this case, we don't have to change it into integers. And we do the same thing, right? We divide 45 by it, like this. And that means we change it into a fraction, and we time it, and we time its reciprocal, right? Divided by number times its reciprocal, cancel out, we get 60. Okay, what this means is that if we don't change them into integers, each part is 60, because originally we don't even have one part, right? We only have 1/6 part, and a 1/3 part, and a 1/4 part. Okay, and then to find out the exact values, we time this number back to the ratios, right? Just exactly the same as we are dealing with integers, right? Dealing with integers, you add them up, you divide, you find out each part, and you time this part back to 2, back to 4, back to 3. You find out the exact numbers, right? So here you do the same thing. Here you time this 60 back to these 3 fractions. Okay, so 60 times 1/6, 60 times 1/3, 60 times 1/4. Okay, it's very easy to see. The first one is 10, second one 20, third one 15. Okay, you see that you have exactly the same answer. And the smallest among all will be 10. Okay, so Jerry Albert. Emma, does that make sense? Okay, yeah. In this kind of question, if you are if you feel okay more comfortable dealing with integers, then of course you can do this. But if you find the second way, just because second way saves us one more step, right? So if you find second way making sense, then yeah, you can just do the second way. Both ways work. Okay. The steps are exactly the same for step one, for method one and method two. Okay, good. See next. Okay, let's read the question first. I'll give you guys half a minute and then see if you guys have any idea. Anyone? We've also done a similar problem in review problems. And I think that was from last class. Maybe you can review it first and see if you have any idea. Okay, and I believe it was another worker problem, which is here. Okay, you see if this makes sense. This is 757. Okay, basically the last problem in the review problems. The question says we have some cooks and they are making omelets in some sort of time, right? So recall that when you so this kind of question, I would like everyone to master this kind of question, okay? Because if you participate in any grade 7, grade 8, or grade 9, mostly grade 7 and 8 math competitions, this kind of problem will definitely be there. Okay, they're called work rate problems. Okay, work rate problems. You have to figure out how to do this kind of problems. Okay, so in this kind of problems, you will always have some people working on something in some time frame. You always have these three factors. Okay, number of people, um, the nature of the job. Okay, the amount of the job, and also the amount of time these many workers take to finish the job. Okay, that makes sense. You have job, you have people, time. It's very logical. It's very practical. In real life, you have the same stuff, right? If you have a project working up, you have 4 people. You're gonna do it for 15 days, something like that, right? You need a number of people. You need the amount of time to do some job. In this kind of question, from 757, we list the information down, right? We have 4 cooks, 10 minutes, and they can make 24 omelets. And then we just see first divided by 4 and then divided by 10. What are we doing? We are working out the individual work rate. Okay, for work rate problems, you always need to figure out what is the work rate of each person. Okay, like one person in one unit of time. Sometimes the unit of time is not minute. It could be hour, it could be day, right? We just need to figure out one person in one unit of time, 1 minute, 1 hour, one day, and how much work they can do, they can finish, they can produce. And then based on the question, you will have like different time or different number of people, and then you can figure out how much work they can finish. Okay, so Jerry, Emma, Albert, that makes sense, right? That just jog your memories. And see this one? It is also a work rate problem. In the first sentence, it gives you the number of people and amount of time and also the job, right? 5 workers, 20 days, and they can build a road. So one road, the same road, in this throughout this question. Okay, so you can work out the individual work rate from that. So I'm gonna list them down and see if you guys have any idea. Okay, so we have 5 workers. Okay, maybe I do a table. So workers, days, and the job we just road. So we have 5 workers, we have 20 days, and then they can finish one road, right? Okay. But now we need to work out the individual work rate as we just discussed, right? Like one worker in one day can finish what percent of the road? Every worker works at the same rate. Okay. So does anyone have any idea? Any idea?
One worker will take 4 days for one road.
One worker will take 4 days to finish one road. Okay, so Albert, let's all think about the first case, okay? So of course, first we need to bring the number of workers down to 1, right? To figure out one individual worker. So if we divide it by 5, now notice that days are time, right? So workers, they need some days to finish one road. So so think about this. If you have 5 workers in 20 days, they can finish the road. What about one worker in 20 days? How much percent of the road or how much of the road they can finish?
1/5.
1/5, right? 1/5. Notice that you don't divide 20 by 5. You divide the amount of job by 5 because people need time to finish jobs, right? So if you divide the number of people by 5, you just need to divide the amount of work by 5, not the amount of time. They need the same amount of time to do to the job of one person, which is 1/5 of the whole work, right? Of the whole road. So here it becomes 1/5. Okay, see if you guys make sense of this. Jerry, Emma, does that make sense? You see, 5 workers, they can finish the whole road in 20 days, right? Then one worker can finish, of course, just 1/5 of the road in the same amount of time. Right, Jerry, Emma? That makes sense? So what Albert was doing so Albert was doing this. I hope I clarify this, Albert. Okay, so that you don't make similar mistake in the future. So Albert was divided by 5 here, and Albert also divided by 5 here, and Albert didn't divide by 5 here. You see, this doesn't make sense because to finish one road, you need 5 workers in 20 days. Now you only have one worker and you also only have 4 days. Do you expect this single guy to finish the whole road? Doesn't make sense, right? It's kind of logical. Okay, so make sure you get a correct logic here. So workers and days, these two are working together, you could say, right? Because you need people, you need time to do one job. Okay, so when you divide it by 5, you only divide the amount of work by 5, not the days. Okay, I think I'll clarify that. Very good. So now we have one worker in 20 days. Then how about one worker in one day, right? To figure out individual work rate, you need one worker in one unit of time. So one worker in one day, right? So one worker in one day, what do we do? Here, one worker in 20 days can finish 1/5. What about one worker in one day? Can finish how much of the road? Anyone?
1 over 5 divided by 20.
1 over 5 divided by 20. So Jerry, Emma, does that make sense? Right? 20 days, you can do 1/5. Then one day you can only do 1/20th of the 1/5, right? Does that make sense? Yeah, it's like if you can do if you can finish say a class in 20 days, then in one day you finish 1/20th of the class. It's very straightforward, right? So here basically you divide by 20, right? 20 divided by 20, so 1 over 5 divided by 20, and that means you have 1 over 5 times 1 over 20, and 1 over 20, right? So in 1 out of 20 days, you can do 1 out of 20 of the whole job. In this case, the whole job is only 1/5 of the road. In this case, it gives you 1 over 100. Okay, so what this means is that one worker in one day can finish 1% or 1 out of 100 of the road. Any question? Good. In other words, it means that 100 workers can finish the road in one day, right? Or one single worker can finish the whole road in 100 days. Okay, so you see, if after we figure out the individual work rate, no matter how many workers or how many days they give us, we can always figure out how much of the road they have finished, or they will have finished after that many days. Okay, and then let's read a question. So now we figure out the individual rate. We work on the conditions of the question. Okay, now we have 3 workers working on the road for 10 days. Before 11 more workers join them. So before 11 more workers join them, we're gonna find out. So before 11 more workers join them, how much work has been finished by the 3 workers in 10 days, right? Okay, so that makes sense. So to help understand this, if you draw a diagram, something like a road, right? Let's say this is the road. So in the beginning, you have 3 workers, right? 3 people. You have 10 days working on the road. So they must have finished some part of the road, right? Say that they finished this part. And for the remaining part, you have 11 more workers. That means you have 14 workers and you don't know how many days, right? So for the remaining amount of work, you know that you have 14 workers. You just need to figure out how many days does it take to build the road. You see, the question is also asking for, well, this answer. Okay, so you guys, does that make sense to you guys? This is poorly written date. Okay, so we're gonna first figure out how much of the work has been finished by 3 people in 10 days. How do we do that? Anyone? It shouldn't be hard because one person in one day can do 1% or 1 out of 100. What about 3 people? What about 10 days? So maybe we can first figure out 3 people in one day, okay? One person in one day is 1 out of 100. What about 3 people in one day?
3 over 100.
3 over 100, right? Jerry and Emma, that makes sense? So Jerry, you do 1%, Albert do 1%, Emma, you do 1%. Altogether, you can do 3%. Does that make sense, right? Okay, so Emma, good? Okay, yeah. So this is basically time by 3. So the amount of work done will come by 3. So here time by, right? So 3 out of 100. Very nice. Okay. But we have 3 people in 10 days, right? So 3 people in one day can finish 3 out of 100. What about in 10 days?
30 over 100.
30 over 100. JVM, that makes sense, right? 3 people in one day, they can do 3%, 3 out of 100. So that means 3 people in 10 days. That means they've been working 10 days, so you time by 10, right? So the amount of work finish will be 30 over 100 times by 10, or in other words, 3 out of 10. Okay, that makes sense? So this tells us that 3 people in 10 days, 3 out of 10 of the entire road has been finished. So that means the remaining part of the work will be 7 out of 10, right? 7 out of 10 of the entire road hasn't been finished. Okay, so 1 minus 3 out of 10 is 7 out of 10. That's the remaining amount of work. Let's just say remaining work, okay? All right. And then to finish this 7 out of 10, we have how many people? 14 people working on it, right? So 14 people here. Now we just need to figure out the amount of days. Any idea? Always think back to the individual work rate, okay? So one person can do 1 out of 100. Then 14 people takes how many days to finish 7 out of 10 work? How do we do this? No idea?
Multiply by 14.
Very nice. Multiply by 14, right? Multiply this by 14. Very good. Okay. So guys, think about this. Again, one person in one day can do 1 out of 100, right? Now we are trying to figure out 14 people takes how long to finish 7 out of 10, right? So why don't we think about, first of all, 14 people in one day can finish how much of the work, right? If we do 14 people in one day, then we just time this by 14. That's going to be 14 over 100, right? And that's very straightforward. Jerry, am that make sense? One person in one day can finish 1 out of 100. Then 14 people in one day, of course, they can finish 14 out of 100. But we don't just need 14 out of 100. We need 7 out of 10, right? We need to find out 7 out of 10. We have 7 out of 10 of the entire work remaining, right? So let's think about, this is in one day. They can do 14 out of 100. Then in how many days they can do 7 out of 10? 7 out of 10 is 70 over 100, right? If you change them, both of them into the same denominator, you will say 14. This is one day, right? So 14 times what? 7. 4 times what number is 70?
5.
5, right? So in one day, 14 people can do 14 out of 100. Then to finish 70 out of 100, which is 5 times the work rate of 14 people, right? And that means you need 5 days, correct? So that means we have, so the number of people is always 14. Here, the the amount of work we need to finish will be 5 times 14 people, what 14 people can do in one day, right? 5 times 14 people can do in one day. That means 14 people need 5 days to finish that. Okay, that makes sense, Kiriyama? Okay, you will see that the whole problem or any work rate problem, this is a work rate problem, okay? Any problem like this, and you will see a lot of similar problems in your math competitions. This kind of question is too hard for school, okay? So you won't see that in school. Actually, in Chinese schools, you get to see them, right? In China, Chinese math is a lot harder than the math here. But here, you won't be able to see it, but you will see similar problems in math competition. So in this kind of question, you always list down the number of people, number of time, amount of time and amount of work. So the relationship, you will see that the relationship is always that if you divide divide number of workers by some number, you're gonna divide your workload by the same number. And also, if you divide the amount of time by some number, you divide your workload by the same number, right? Because workers need time to finish job, okay? And if you need to time them, sometimes you need to time them, right? Then you time with when you time the number of workers, you time the amount of work. Or if you need to time the amount of work, you need to time either the number of time, the number of days or amount of time, or number of workers. Okay, so the relationship is that workers and they are in a group. If any of them do multiplication, say times two, then the work you have to time two. Okay. And if you divide, say that you divide the work by a number divided by 3, then for days you're gonna divide it by 3, or for the number of workers divided by 3. You have to choose one. Okay, so based on the question, you try to list out your numbers, and then the relationship is just that you time these two, you time the work. Okay, you divide these two, you divide the work. So sometimes the work is given, sometimes the time is given, sometimes people is given. You don't know which is given. Okay, so based on different questions, you have to work out the missing numbers. Okay, so another way to ask this question is that, for example, you can say, if 3 workers work on a road for 10 days, and then some more workers join them, and say the company needs the road to be finished in 5 days, how many more workers are needed? They can also ask in this way, right? In this fashion. Does that make sense? In this case, you're given the time, but not the people. Okay, they will say that the road needs to be finished in 5 days. It gives you time, 5 days, and it will ask you how many more workers are needed. Then you will, based on this 5, you will see that the remaining work is 70 out of 100, right? You only have 5 days to finish that. So in 1 day, you have to finish 14 out of 100. That means you need 14 people, because one person can only do 1 out of 100. And that means you need to have 11 more people. Okay. So yeah, there were many ways to ask the same type of question. You always just need to make this table, find out the missing value. Okay, I hope we are good. Okay, if you have any questions, let's look at the next problem. Okay, maybe we can do this algebra question first. It's much shorter. Okay. Equation is given. Any idea?
We need to think that what squared equals to 16.
What squared equals to 16? Okay. Yeah. So what squared equals 16?
This is 4, so x equals 4.
Yeah. Okay. So if x is 4, this is 16, and this is 4, and that's it, right? Okay, but does this always work? What if I change this to say 25? Then if you make x to be 5, you see, that's not equal. Okay, in this question, yeah. So in this question, if you just figure out x squared is 16, it worked, but it doesn't always work. Okay, so any other idea that can always work? What are ratios exactly? Ratios can be changed into what? Ratios are, you guys remember?
Fractions.
Fractions. Very good, right? Jeremy, am I right? ratios are actually fractions, right? So why don't we just change them into fractions and then solve the equation? Remember in chapter 5, we learned how to solve equations, right? Okay, so in this kind of question, we always change the ratio into fractions and solve the equation. So if you change them into fractions, 4 over x squared equals x over 16. Okay, then this is from chapter 5. A fraction equals a fraction. How do we solve this? There's a technique called what?
Cross multiply.
Cross multiply, right, Jerry Emma, remember? If you have fraction equals a fraction, you cross multiply, right? So this times this times this. Okay, so what do we have? 6 times 4 times 16, that's 64. X times x squared, that's x cubed. So that means we just need to figure out what number cubed is 64, and that's 4, right? To think about this is, I mean, this is like square root and cube root. We haven't really reached that far, but this is very simple number. So it's a very simple number, so we can figure it out. I mean, 64, obviously, that's a bunch of 2s, right? 2 times 2 times 2 times 2. And then you can easily figure out that's going to be 4. Okay? You said this works for any number. Okay, Albert, that makes sense? Because even if I change 16 to any other number, say I change 16 to 10, I change this for, I don't know, to 100, whatever, you can always cross multiply, you get 1,000 equals to x cubed. In this case, x is 10. Okay, so you don't have to always work out like what x squared can be 10, right? If I change this to 10, if you try to think what x squared, what number squared is 10, that doesn't really give you any result. Okay, yeah. So yeah, ratio equals ratio, very easy. Change to fractions and cross multiply. Okay, for other numbers, say that this is 65, then you won't be able to find an integer, and we will talk about this kind of situation in next few chapters. Okay, they're called square roots, cube roots, they're called roots. That's equivalent to math 9 or math 10 in school math. Okay. Okay, good. Not bad. So yeah, one more word problem. Let's see. Now it's 9:20. We have 20 more minutes. Let's do one more question and we talk about chapter 8. This is quite a long question, right? I'll give you guys again have a minute to 1 minute. Okay, does anyone have any question regarding the meaning of any sentence? Emma, can you understand this? This is not a 100-meter race. This is only a 60-meter race, okay? Right? We have 3 guys. So this is the racetrack. It's 60 meters. when Paul finished it, right? So Paul is here. He was ahead of Robert by 10 meters. So where's Robert? Robert is at 50-meter point, right? The Robert is here, and then Sam is here. They're separated by 10 meters and then 10 meters. So Paul obviously just finished. And then after Paul finished the first, Robert and Sam, they're gonna continue to finish the race. So the question is asking, when Robert finished the entire race, where's Sam, right? By how many meters is Sam behind Robert when Robert finished the race? And their rate of speed don't change. Any idea, anyone?
Can we change it to like 1/10 per meter?
When 1/10 per meter? What do you mean? 1/10 what per meter?
Oh, is this like the work rate problem?
Yeah, sort of. Sort of. As yeah, you could see it as a work rate problem, but here people don't actually work together, right? It's just that Robert is gonna finish his job. You know, his job is to finish the 60-meter race, and Sam has to finish the same race, right? So yeah, it's sort of like a work rate problem. We can compare the rate of Robert and the rate of Sam, right? And how do we compare them? So by the time when Paul finished the race, we could figure out how many meters has Robert finished and how many meters has Sam finished by the time Paul finished the race, right? And that means we can figure out the amount of work. It's sort of like sort of similar to the amount of work done by Robert and also the amount of work done by Sam in the same amount of time. And that's a comparison between their work rate, or in this case, between their rate of speed. Okay, so let's list this down. When Paul finished the race, how many meters has Robert finished? How many meters has Sam finished? It's from the diagram. Anyone? When Paul finished, Robert is 10 meters behind, right? The entire racetrack is 60 meters.
Robert is at 50
Yeah. And
and
Sam?
Sam is by 40.
40. Good. That shouldn't be hard, right, Jerry Emma? That makes sense? So when Paul finished, Robert is 10 meters behind. So Robert finished 50 meters and Sam is 20 meters behind. So Sam finished 40 meters, right, Jerry Emma? And Robert and Sam, they finished 50 and 40 meters respectively in the same amount of time, right? In the same amount of time. Okay. So now we can compare their work or work rate, doesn't matter. In this case, because they finished they finished these many meters in the same amount of time. Now we can just figure out the ratio between them. It's 50 to 40, right? 50 to 40, or in other words, 5 to 4. What does this mean? This means that uh when Sam run, so basically for every 4 meters Sam runs, Robert is gonna run 5 meters. Does that make sense? This ratio tells us because their speed never changes, right? So the ratio here tells us that whenever Sam runs 4 meters, Robert runs 5 meters. Does that make sense? It's a comparison between their meters, right? 50 to 40. So that means, okay, I'm going to write it down. So whenever, well, R runs 5 meters, Sam runs 40 meters. No, 4 meters, sorry. Does that make sense to you guys? Right? 50 to 40, 5 to 4. So if Robert runs 10 meters, Sam runs 8 meters, right? If Robert runs 50 meters, Sam runs 40 meters. If Robert runs 100 meters times by 20, then Sam would run 80 meters. Does that make sense? Right? It's a comparison, it's a ratio between their work, you could say, right? Between their race, between their distance they covered, the distance they covered. Okay, make sense?
Yeah, but Sam is behind 20 meters.
Yep.
But is it 30 meters? Not 40?
30? Oh,
Me-
Sam is behind Paul by 20 meters, not Robert. You see?
Oh, okay.
Yeah. So when Paul crossed the finish line, and he means Paul, right? Paul was ahead of Robert by 10 and ahead of Sam by 20.
Oh,
So
okay.
Sam is only only behind Robert by 10. Mhm. Okay, so this makes sense to everyone, right? Now Paul is out of picture, right? Paul has finished. We just wipe him out. So look at the diagram. The question is asking when Robert finished the race, how many meters is Sam behind him, right? So the question is, how many more meters does Robert has to finish, has to cover? When Paul finished, Robert was 10 meters behind, right? So that means how many meters are there for Robert to cover? Well, that's not a math question. It's just the understanding of the problem, right? When Paul finished, Paul has finished here, okay? When Paul finished, Robert is 10 meters behind. So how many more meters does Robert has to cover if Robert were to finish?
Yes, 10 meter to cover.
Just 10 meters to cover, right? It's based on
Yeah.
the question, right? So after Paul finished, Robert has 10 meters to finish, right? To cover, to finish. So that means Robert has to run 10 meters more, right? So if Robert runs 10 meters more, then during the same amount of time, how many meters can Sam run? Whenever Robert runs 5 meters, Sam can run 4 meters, right? So if Robert runs another 10 meters, how many meters can Sam run?
8.
8 meters, right? Because it's 5 to 4. Okay, it's sort of like R to S, a ratio here. R to S is 5 to 4. And now Robert has 10 more meters to run. And for Sam, it's a question mark, right? So obviously, we just time by 2. We can figure out that Sam has 8 more meters to run. Does that make sense to you guys? Okay, so Jerry, Emma, that makes sense? And then that would be the answer here, okay? So before we talk about the answer, let's go over the method again, okay? So first we understand the question and we draw a diagram or whatever, okay, just whatever way, by whatever means you understand the question. And then you will see that when Robert finished 50 meters, Sam only covered 40 meters. And this is the time you can set up a ratio. So in other words, this is the time you can set up a ratio. R to S is 5 to 4, or you can use fraction. Doesn't matter, right? Fractions are ratios. Okay, depends on which way you prefer. Okay, you can do fractions, you can do ratios. So this means that for every 5 meters Robert covers, Sam can cover 4 meters. Okay, and then again, based on the question, we will see that Robert has 10 more meters to finish, to cover. So that means if Robert covers that 10 meters, and Sam would cover 8 meters in the same time. Okay, so that means during the last part, during the last 10 meters, Sam would have, well, 2 more meters behind Robert, right? And at this point, Sam is 10 meters behind Robert. So 10 plus 2, you get 12. 12 is the answer, right? At this time, Sam is 10 meters behind. And by the time Robert finished the race, we said that Sam only covered 8 meters, right? During that same amount of time. So Sam is around here. Sam finished 8 meters. So that means Sam has like 12 meters in this part. Okay, Sam was behind by 10 meters. And during the last part, he's further behind by 2 meters, right? 8 to 10. So in total, he's 12 meters behind. Okay, and then 12 meters will be the answer here. So in the end, you could say 10 minus 8, that's 2 meters difference, right? And then 2 meters plus the 10 meters he has already been behind. So the answer is 12 meters. Okay, Albert understands. Very good. Jerry, Emma, make sense? Okay, good. Very nice. Very, very good. Yeah, so, okay, very nice. So we have 4, 5. Only 5 questions to go. Maybe next time we can finish them. Okay, so let's move on to chapter 8, talk about a few problems here. For the example problems, you guys did a really good job on these ones. And Emma has some problem here. Let's talk about them. So this. Okay, Emma, this is the problem we have. 1/3. Now in this chapter, since you guys have previewed, you will see that percentages are basically the same as fractions, right? Percentages are just some numbers over 100. So for F, that's 1/3. So 1/3. So Emma, do you remember how to convert them into decimals? To convert 1/3 to decimals, you divide, right? You divide 1 divided by 3. So you get a 0 and get a 0 here. And you get 3, and 3 times 3 is 9, right? And another one. And another one tells you that's another 3, right? And just goes on forever. So 1/3 is 0.3333. 0.33 repeated. Right, Emma? Okay. So to convert 1/3 to decimals, you get 0.3 repeated. And then to convert this to percentage, well, I believe you know how to convert them to percentages, right? Because for the other questions you got them, basically just time by 100, right? Because you have to divide by 100. Percent means means something over 100, right? So if you need to divide by 100, you have to time it by 100. You just move the decimal point to two places, right? So if you move it 2 places, there will be 33.3%, 0.3 repeated like this, okay? So 33.3 repeated percent. Or if you want, you can do 33 and 1/3 because, 3 repeated is 1/3. So both will be acceptable. Okay, Emma, make sense? So for fractions, we just, we always convert them into decimals and then move decimal point 2 places behind, to the right, to convert the number into a percentage, into a percent. Okay. So yeah, Emma, you might want to make a note, okay? And then we have FGH. Okay. Oh, so to convert decimals to percent, that's a problem. Okay, here. Let's see. Okay, so Emma, maybe I should explain these first, okay? Because once you understand how to convert decimal to percent, you can always convert fractions into a decimal and then convert that into a percent. Okay, so let's see. 0.33. So to convert a decimal into a percentage, you always move the decimal places to the right by 2 places. And that's it. Okay. Why? Think about this, Emma. If you have 0.33, you want to convert into percent. A percent is something over 100, right? Basically like this. Something over 100. What is that thing? What is that number? You don't know, right, Emma? If you don't know, you can always suppose to be X. Remember? Right? So basically, any kind of this kind of question, no, a decimal equals to some percent, it always give you an equation like this. And you will see that to figure out X, you just time by 100. You time by 100, 100 is gone, time to the other part, 0.33 times 100. That's just equivalent to moving decimal places, the decimal 2 places to the right, which is 34. The first one is 34%. Okay, so Jerry Albert, does that make sense, right? Yeah, you always suppose X, you would say just time by 100. So the next question, Emma, again, this is 0.081 equals to X over 100, right? Some number over 100. So that number is this number times 100. So you move it 2 places to the right. That's going to be 8.1%. Okay, so Emma, for the last one, could you do it to see if you understand? Always move your decimal point 2 places to the right. What do you have?
Negative 21.9.
21.9. You move it 2 places.
Oh, yeah. Negative 290. Wait, 219.
Yes, negative 219%. Very good. Okay, remember? Does that make sense, Emma? Every time by 100. Move the decimal 2 places to the right. That's it. Okay. Yeah. So that's why this 1/3 convert to decimal, you can do this. If you don't convert to decimal, you have to change this to 100. Yeah. You can do that too. So I'm gonna maybe talk about this once more. So this you can convert into a decimal and move it 2 places to the. So you can do this. Or another way is that if you have a fraction and you need to convert it into something over 100, you get the same equation again, right? So 1/3 equals to, again, you don't know the number here, but it's over 100, right? So again, cross multiply, right? So cross multiply, you have 3x equals to 100. Then obviously you just divide by 3, x is 100 over 3. That's it, okay? So x is 100 over 3. That means 1/3 is 100 over 3%. And also, if you want to change it into a mixed number, that's 33.3%. Repeated. Sorry, mixed number. 33 and 1/3%. Okay? And any format is acceptable. You can do this. You can do this. Or if you want, you can do this. Okay? Anything is okay. So Emma, that makes sense? You always, no matter you have fractions or decimals, you're always equal to a number over 100 because a number over 100 is a percent, right? You just need to figure out this number. You suppose it to be X. But most of the time, you can just see it, right? Because most of the time, something like over 100, over 4, over 5, or over 10, the denominators are factors of 100. You can just time by that number, so it's easy to see. Yeah. Okay, let's see. One last problem, D. In homework, I see that this is also one of the problems for Jerry. Okay, Jerry, you got one homework question wrong, and it was a similar problem to this. Okay. So what is 1/4% of 1,000? This kind of question, we always just multiply them, right? So when we multiply them, don't mistake 1/4 as 4, okay? So when you write down your equation, 1/4% times 1,000, right? And then when you do this, recall that this percent mark is always over 100, right? So divided by 100. So this part divided by 100 times 1,000, that gives you 10. Okay, but let's make it clearer. 1/4. The percentage, you can always see it as 1/100 divided by 100, okay? And then times 1,000. That's just the key here. So you cancel it out. This is 10, 10/4. The answer is 10/4 or 5/2. Okay, I remember in Jerry's homework and also Albert, I remember, well, I'm not sure if I'm correct, but I remember that you also have a similar problem here. So I remember that you guys got the question wrong because you were doing like 1/4, you're doing 4, but it's actually 1/4. Okay, so make sure you put all the numbers correctly, and that's it. Okay, let me have a look. Okay, maybe not Albert. Albert is another one. See, Albert, this one, when you convert this number into a percent, you always move the decimal point 2 places to the right. In this case, you didn't. You were having the same number, you see? You have to move it 2 places to the right, so it becomes 19250%. It's 19,000 something, okay? And that's gonna be, let me see, Jerry. Yeah. Yeah, here. Okay, Jerry, that's the problem. Yeah, so Jerry, that's the H. 1/5% of 2,000. You see, that's the same question, right? The question we just talked about is 1/4% of 1,000. Okay, so the reason why I got this, I believe, is because you used 5 instead of 1/5. So you're greater than yeah. You can have a look and correct it. Okay.
Okay.
Yeah. All right.